We are starting this video with our example of a loop in a magnetic field, and we are looking at the torque that the loop is experiencing due to the magnetic field. So I uploaded, this is at the end of the first solutions document, and the last example wasn't added, so I have a separate file and it's called torque on a current carrying loop example. So this example right here is a JPEG that I uploaded on D2L. That's a pretty straightforward example, just a couple calculations, but there's a little trick in here with the angle that we have to talk about. So we have a rectangular loop of 100 closely wrapped turns. So this is actually a coil. So this is a current carrying coil, and what we have to do is we're going to use that expression for torque, which is the current passing through the loop times the area that the loop makes times the magnetic field times the sine of the angle between the area vector and the magnetic field vector. So at the end of the last video we talked about creating this area vector so we could use the right hand rule, and we could in some cases we could easily identify the angle between the area vector and the magnetic field vector. This is for a single loop, right? So this expression is for a single loop. If I have a coil which consists of n turns, right, or n loops, then I would just take this expression and I'm going to multiply it by the number of loops. Okay, so this is for a single loop. If I have n turns in a coil, say 50, 100, something like that, I'm just going to take this and I'm going to multiply it by n. Alright, so I'm going to show you how we do that in this example. Second, we have to kind of draw a sketch. I drew a bird's eye view of this loop, like I did, or like this slide has, right? So I've got kind of a bird's eye view. This is going to help me identify the direction of the area vector, and then it's going to help me calculate that angle. But this diagram is kind of hard to see, right? It's very tempting for me to just say, oh look, oops, sorry. Oh look, I got an angle right here, it's 30 degrees. I bet that's the angle that I'm supposed to use. So we'll see that we have to use a different angle than this once I draw this a little bit differently. So the loop has a current of 1.2 amps. There are 100 loops inside this coil, and it's a rectangular loop, and the sides are 0.4 meters by 0.3 meters. So these two sides are 0.4 meters, and then the top and the bottom are 0.3 meters. So we're looking for the magnitude of the torque exerted on the loop. We have a magnetic field strength of 0.8 Tesla, and the magnetic field is pointing in the positive x direction. It says it's directed along the x-axis, so we're going to say the magnetic field is pointing in this direction. So I think I'm in pretty good shape. I've got all these quantities, right? I can use NIAB sine theta. Here's my problem. I've got the current, I've got the dimensions, right? I've got A, I've got B, so I can find the area. I've got the magnetic field strength. So I drew a view from the top. I drew a bird's eye view of the loop. So we're looking down at the loop right now. Here's the x-axis. Okay, here's the x-axis. This is the angle that is marked in the diagram, 30 degrees. The angle between the x-axis and the loop. But this angle is not the angle between my area vector and my magnetic field vector. Okay, so I have to draw that area vector, which is perpendicular to the area made by the loop. Okay, so that surface made by the loop, I'm going to draw my area vector perpendicular to that. And so if this area vector is perpendicular to the loop, that angle's 90. The angle in the diagram is 30. This has to be 60 degrees. So I'm actually looking for this angle because I know the magnetic field is directed along the x-axis. So there's a big magnetic field pointing in the positive x direction. So these two angles right here that I have both marked 60 are alternate interior angles. And if you remember from geometry and maybe a couple of physics problems in the last couple weeks, you know that they are congruent if these two lines are parallel. So we know the magnetic field vector is parallel to the x-axis. So that is 60 degrees. So the angle that we're using in our IAB sine theta expression is actually going to be 60 degrees. So we're using the angle between the area vector and the magnetic field vector. There are n loops inside the coil, so I'm going to use n I a b sine theta. All right, I've got 100 turns, that's n, 1.2 amps, that's I. The area enclosed by the loop is the length times the width, 0.4 meters times 0.3 meters. Magnetic field strength is 0.8 Tesla, and the angle between my area vector and my magnetic field vector is 60. So when I calculate this, I get a torque of 10 Newton meters. Remember, our torque is force times displacement units. So it's Newton meters. And so what I'm going to do is, they were also asking what's the direction of the rotation of the loop when it experiences this torque. So I'm using the right hand rule. I'm going to point my fingers, the fingers of my right hand, I'm pointing them in the direction of the area vector first, because it's A cross B. It's A cross B. So I point my fingers in the direction of the area vector, and I'm going to curl them in the direction of the B vector. Okay, so my thumb, in order to do this, my thumb is pointing into the page. My thumb's pointing into the page, and my fingers are pointing in the direction of A. If I curl them in the direction of B, then I'm curling them in the clockwise direction. So the direction of the loop's rotation is going to be clockwise as viewed from above. Right? So if I'm looking at this loop from above, I'm going to notice that it rotates clockwise. So I use this formula to calculate the magnitude, and then I use the right hand rule and apply it to A cross B to find the direction of the torque, the direction of the rotation that the loop has. Okay, so I'm pretty sure this is very similar to a WebAssign problem. So the biggest issue I see is picking that angle. Okay, so draw a different diagram, maybe look at it from the top, and then draw another diagram and use some geometry to figure out what that angle is between the area vector and the magnetic field vector. So chapter 19 is, as you can tell, a pretty extensive chapter. So we're going to have quite a lot of material in chapter 19. But so far it's all been related to how moving charges behave in a magnetic field. But earlier in chapter 19 we talked about how if we took a compass and we put it in a magnetic field, then it would align with the direction of that magnetic field. But we also see something similar happen if I have a wire and it's carrying current, and I take a compass needle and I bring it close to the current, the compass needle deflects. And as I put it at different locations around this wire, it's going to point in a direction that's tangential to a circle around the current. Right? So picture I have a compass needle right here. The north end is going to point up. I move it here. The north end is going to point in this direction, and it's going to keep doing that. right? The compass needle is going to keep deflecting as I move it around this current carrying wire. Now this current is going into the page right now. So this tells me that a current carrying wire actually generates a magnetic field around it. Now in this diagram, these arrows are much larger down here than they are outside. So this diagram shows me that the magnetic field actually gets weaker the farther away you are from the current carrying wire. Okay, so it gets weaker as you go farther away, but the magnetic field is always going to be pointing in a direction tangential to the circle at that location. So you see the magnetic field is kind of going in a circle. And it gets weaker the farther we go out. Okay, but since the magnetic field vectors are changing directions, we can kind of picture them, the magnetic field is going around in a circle. Now in this case, the magnetic field is traveling or is pointing clockwise, right? So if I took all those vectors and I connected them together, I'd see that the magnetic field lines are actually circles around the current carrying wire. So this current is going into the page, and I see that the magnetic field is clockwise around the wire from this view. If I change the direction of this current, you could probably gather that if the current was coming out of the page, then the magnetic field would go counterclockwise. Okay, so the direction of the magnetic field is dependent upon the direction of the current in the wire. And this is our third right-hand rule. So we're going to use our third right-hand rule to determine the direction of the magnetic field generated by a current carrying wire. Well, the first thing I'm going to do, and don't try this at home, hopefully you don't have any exposed wires that you can grab at your house, but we're going to picture a current carrying wire, and we're going to grab that wire. Okay, so anytime you see a diagram with a wire, you're going to pretend that you're grabbing that wire with your right hand. And when you grab the wire with your right hand, you want your thumb to be pointing in the direction of the current. Okay, so this is my right hand rule. My right thumb is going to be pointing in the direction of the current, and I grab the wire. So as I grab the wire, I'm curling my fingers around the wire. And so my fingers are kind of making a circle around that wire. So the direction that my fingers are pointing in, notice that your fingers kind of make a circle, so at different locations it's a different direction. But the direction that I curl my fingers around the wire tells me the direction of the magnetic field. So whatever circle you make with your fingers, with your thumb directed in or pointed in the direction of the current, that's the direction of the magnetic field at any location outside the wire. And so the magnitude of that magnetic field is given by this expression here. So it's directly proportional to the current. So the greater the current going through the wire, the stronger the magnetic field. It's inversely proportional to the distance between the wire and some point outside. So this distance here would be r. Okay, so that's a nice little, that's a circumference term right there, right? 2 pi r. So the farther out you are, right, the farther out you are, you're making a larger circle. Okay, and so the farther out you are, the weaker that field gets. So it's inversely proportional to the distance between the wire and some point from the wire, and it's directly proportional to the current going through the wire. So mu naught is the permeability of free space. If you remember from chapter 16, I believe, or 17, when we were talking about capacitors, we talked about the permittivity of free space, which was the ability for an electric field to propagate through free space. So this is the ability of a magnetic field to propagate through free space. So mu naught is the permeability of free space. And so that's 4 pi times 10 to the negative 7. We're in units of Tesla meters per amps. So our amps are going to cancel, our meters are going to cancel here. I'm going to be left with Tesla. And so what you'll see is this 4 pi and this 2 pi. Usually what I do is I'll write it out. I'll substitute this value in, and then I'll reduce that 4 pi over 2 pi, just because they're really nice and we can cancel those out. Help me with my calculations. So we'll do a basic example here. We've got a 1 meter long nichrome wire, and it's got a diameter of 1 millimeter. So it's connected to a 12 volt battery. We want the magnetic field strength 1 centimeter away from the wire. Now in these examples we can neglect the length of the wire. We're really just concerned with our position relative to the center of the wire. So the first thing I want to do is, if I go back to this equation, I got to find the current going through the wire. Right? I have the location that we're concerned with. Okay, 1 centimeter. So we're 1 centimeter away from the wire. That's our R. Right? That's our distance. But what we don't have is the current. Right? We don't have the current. So we do have the length of the wire. We've got the voltage applied across the wire, and we know what it's made out of. So I think there's something we can do here to find the current. So we also have the diameter. Right? You get the diameter of the wire. So the first thing I'm going to do is I want to find the current. Right? I want to find the current through the wire. I've got the length of the wire, the diameter of the wire. Okay, sorry, I had to pause the video there. So we've got the length of the wire, we've got the diameter of the wire, and we've got the voltage. So I looked up the resistivity of nichrome. So if I have the length, I've got the diameter, so I can calculate the area. I looked up the resistivity, so I'm going to find the resistance of the wire, capital R. So I'm going to find the resistance of the wire, and then I'm going to use Ohm's law to calculate the current. And then once I have the current, I can use this expression right here to calculate the magnitude of the magnetic field at that location, 1 centimeter away from the wire. So I've looked up the resistivity of nichrome. I'm using the diameter to calculate the area. We'll just model it as a cylindrical wire. If they don't specify, we'll just assume it's a cylinder again. So it's pi times half the diameter squared, and I get a cross-sectional area of 7.85 times 10 to the negative 7 meters squared. So now that I have the area, I've got the length and the resistivity, I can plug that into my expression for the resistance, and I get the resistance of the wire, 1.91 ohms. So a little bit of, chapter 17 stuff coming back to help us out here. So now that I've got the resistance, I'm going to use Ohm's law to find the current in the wire. So V equals IR, solve Ohm's law for I. I've got the voltage, 12 volts, divided by the resistance. Now I've got the current, 6.28 amps, passing through the wire. Now that I've got the current, I know I'm 1 centimeter away. I have the permeability of free space available to me. I've got the current divided by 2 pi times the distance, right, the R vector, which is 1 centimeter. So when I calculate the magnetic field, I get 1.26 times 10 to the negative 4 Tesla. Very weak magnetic field, but there is a field there nonetheless, close to the wire. Okay, and we see that if this got larger, right, if the current got larger, we'd have a stronger magnetic field. Okay, so we've been talking about magnetic field as a vector, right? Now, this is one of the most challenging parts, is recognizing the direction of the magnetic field at some location. So we have to use the right-hand rule, but it also helps to like draw a diagram out to identify the direction of a magnetic field. Let's say I had two wires next to each other, right? If I had two parallel wires and they were both carrying a current around them, or a current through them, and if I was right in between those two wires, there would be a magnetic field due to both of those wires. And since magnetic field is a vector, we can use the principle of superposition to add the magnetic field vectors, just like we did with force vectors in 120. So we're just adding them up. We'll have to probably resolve them into x and y components and do all that fun vector algebra we used to do. Okay, so the superposition of magnetic fields. All right, now again we're dealing with life in 3 dimensions. Okay, so we're going to have stuff going into the page, coming out of the page, all that stuff. So I've got 2 wires, right? I've got 2 wires. So the first wire has a current of 5 amps going in the positive y direction. The second wire has a current, same current, 5 amps, but that's in the negative y direction. So I want to find the magnitude and the direction of the net magnetic field due to both the wires at points P1 and P2. So let's talk about point P1 first. Okay, let's talk about point P1 first. There is a magnetic field at this location due to this wire and due to this wire. So let's use the right-hand rule for the wire on the left. Right, let's use the right-hand rule for the wire on the left. If I use my right hand, my thumb is pointing in the direction of the current. So my thumb is pointing in the positive y direction. So I'm curling my fingers around. Okay. Now if I'm looking down from above, you see that my fingers are going to be curling counterclockwise around the wire. If I'm looking down at the wire, I grab the wire, my fingers are curling counterclockwise. So that means at P1, my fingers are going into the page. Okay, so I know this is a challenge with me not being there, but pretend you're looking down at the wire, grab the wire with your right hand, you'll see that your fingers are going into the page on this side. They're coming around counterclockwise, and then they're coming out of the page here. Okay, and then back again, right? So a counterclockwise loop around this wire. Okay, only talking about this wire right now. I'm not talking about this one over here. So the magnetic field at P1 due to this wire is into the page. Okay, it's into the page. If I do the same thing with this wire, I'm going to grab it with my right hand still. I'm still going to grab it with my right hand, but now my thumb is pointing down. So if I'm looking down at the wire from above, grab the wire, my fingers now are rotating clockwise around the wire as I'm looking down at it. So that means my fingers are going into the page on this side, and then they're coming around this way clockwise, and on this side of the wire they're coming out of the page. So the magnetic field at P1 due to this wire is into the page, the negative z direction. The magnetic field at P1 due to this wire is out of the page, or the positive z direction. Now what we also notice is that this wire is closer to P1 than this wire. So I actually have two R values, two different R values. So when I'm calculating the magnetic field, I have to use 20 centimeters when I'm dealing with this wire, and I have to use 10 centimeters when dealing with this wire. So let's calculate it, and what I'm going to do is I'm going to say the magnetic field due to this wire is positive because it's coming out of the page. So I'm going to give this a positive sign, and then this is into the page, so I'm going to make that negative. I also see that the magnetic field here, or due to this wire, is going to be weaker because it's farther away. The current is the same, but it's farther away from this point, so it's going to be weaker. So I'm expecting a net magnetic field in the positive y direction, because I'm expecting the B field due to this wire to be stronger than the B field due to this wire. So let's check it out. So this is an example. I must have accidentally deleted the slide, so I will come back and I'll try and find that example and walk through that. So we are actually on, this is slide 25. Okay, so this is our solution to this problem right here. Okay. So I'm looking for the net B field at P1. So I'm calculating the magnetic field due to wire 1 and the magnetic field due to wire 2. Okay. So notice I'm looking for the magnitude of the B field due to wire 1. I have to use 20 centimeters for R. So I use mu naught I over 2 pi R. So wire 1, I'm calling the wire on the left wire 1. It's 20 centimeters from P1. So permeability of free space times the current divided by 2 pi times R, and R is 20 centimeters. Okay. So if you notice, again, the pi's will cancel. I've got two, actually I've got 4, and then I've got these two 2's which cancel out. So that'll help me with my calculation to avoid errors. Okay. So when I calculate this, I have the net magnetic field of 5 times 10 to the negative 6 Tesla. That's into the page, so I'm going to call that's the negative z direction. Alright, so when I add them up, I have to make sure that I give this a negative sign. The magnetic field due to the wire on the right, B2. Same current, mu naught's a constant, 2 pi. The distance between that wire and P1 is 10 centimeters, right? So it's stronger, right? So it's a stronger magnetic field. So I'm going to use 10 centimeters for R here. When I calculate it, I get 1 times 10 to the negative 5 Tesla. So that's twice, right? 1 times 10 to the negative 5 is twice the magnetic field strength due to B1, which again makes sense. It's half the distance from P1 as the left wire is, so I expect the field to be twice as strong. Now our right hand rule tells us that's out of the page, so that's the positive z direction. All right. So B net is going to be B1 plus B2, but I have to remember that B1 is negative. So it's actually B2, 1 times 10 to the negative 5 Tesla, minus B1, because B1 is into the page, the negative z direction. And so I get a net magnetic field of positive 5 times 10 to the negative 6 Tesla, and that's out of the page. So those are two ways that you can describe the direction. Into the page, negative z direction. Out of the page, positive z direction. So let's do the same thing for point 2. We still have the same current, right? We still have the same current, but when we did our right hand rule, right? We did our right hand rule for this left wire. The magnetic field was going into the page on this side. We saw our fingers were curling around the wire in the counterclockwise direction if I'm above it looking down. So on this side of the wire, the magnetic field due to the left wire is actually coming out of the page. So this magnetic field is going to be positive, out of the page, the positive z direction. We do the right hand rule for the wire on the right. We see that the magnetic field due to this wire was coming out of the page here at P1, but it was looping clockwise around the wire, right? My fingers were looping clockwise around this wire. So on this side of the wire, the magnetic field is going into the page. So now the magnetic field due to this wire is positive. The magnetic field due to this wire is negative. Again, we have to deal with different distances, different R values. The distance between this wire and P2 is 20 centimeters, just like it was over here. But now this wire is 30 centimeters. So I have to take 10 centimeters plus 20 centimeters, use that as my R value to calculate the magnetic field due to this wire. So at P2, the magnetic field strength due to the wire on the left is positive out of the page. So we see that it's the same value, right? Same R, same current, all my constants are still the same. So when I calculate, I'm still using 20 centimeters for R. So I get 5 times 10 to the negative 6 Tesla, but this time it's out of the page. Okay, so B1 is now positive at point P2. And the magnetic field due to the wire on the right is going to be negative because it's going into the page. My R value when calculating B2 is different. Again, same current, mu naught 2 pi. My distance is 30 centimeters, right? 10 plus 20. So I have to use 30 centimeters for this R value. So when I calculate the magnetic field strength, I get 3.3 times 10 to the negative 6 Tesla. Weaker because it's farther away than P2. That's good. That makes sense. But it's into the page, right? It's going in the opposite direction on the other side of the wire. So this value is negative. Into the page, the negative Z direction. So I'm adding B1 and B2, keeping in mind that B2 is in the negative Z direction. So it's actually B1 plus, it's 5 times 10 to the negative 6 Tesla minus 3.3 times 10 to the negative 6 Tesla. And again, I have a net magnetic field that's positive. So the net magnetic field is out of the page. And its magnitude is 1.667 times 10 to the negative 6 Tesla. So this is kind of a good, like a one-dimensional magnetic field vector problem, because our B fields are either going into the page or out of the page. So it's a nice like one-dimensional magnetic field addition problem. Here's that problem. There it is. Okay, sorry about that. I'm doing this a little backwards. So the solution that I skipped, I actually skipped the slide too, so I didn't realize that I skipped it. So sorry for hopping around and stuff. Actually, what I'm going to do is, hopefully this will help us not get too confused. So I'm probably sitting at 40 minutes or so. So I'm going to stop this video. I'll come back and I'll do this problem, and then I will do 2 more magnetic field superposition problems, and we will officially be done chapter 19. Okay, thanks.